The blades of wind turbines rotate so slowly. How exactly does it generate electricity? Let's first take a look at the blades, how they start to rotate. If you look closely at the cross-section of a blade, you'll find its shape looks like this. It is similar to an airplane wing. When the wind blows, the air flows faster on the upper surface of the blade and slower on the lower surface. According to Bernoulli's principle, at this time, an upward pressure difference is generated on the blade. This pressure difference is lift force, which pushes the blade to rotate. Since the blade length can reach over 100 meters and the blade root is very thick and wide, it gradually becomes thinner and narrower towards the top. This design allows the blade tip speed to reach 210 to 255 kilometers per hour. At such a high speed, if it rotates too fast, it would snap the blades directly. Therefore, the blade speed of a wind turbine is generally controlled at around 15 revolutions per minute. Then how is this rotation speed controlled? Actually, it's very simple. Just adjust the angle of the blades. Let's look at the connection point of the blade. There is an integrated bearing mechanism here. The outer ring of the bearing is bolted to the hub, the inner ring is bolted to the blade. This kind of bearing can allow the blade to rotate around its own axis. There is a motor at this position below, with a rated speed of about 1500 RPM. There is a gear on top of the motor. The gear meshes with the gear of the bearing's inner ring, but the torque generated by the motor is not enough to directly drive the massive blades to rotate. Therefore, on the output shaft of the motor, 2 stages of planetary gears are installed to achieve deceleration and torque increase. When the power is finally transmitted to the bearing, it can rotate the blade angle and thus control the rotation speed of the blade. Each blade has such an independent motor to achieve independent control of the blades. This hollow 3D structure is the hub. There are 5 large circular holes on the hub. In addition to connecting the 3 blades, because resistance will be generated here at the front, a nose cone will be installed. The nose cone is usually made of fiberglass. It can prevent corrosion and weathering. At the same time, for the oncoming wind, the nose cone can also guide them better to the blades onto. The circular hole at the back connects to the drive shaft. This shaft in the middle is the drive shaft. It is used to transfer the torque generated by the blades towards the back. The drive shaft is supported by 2 bearings. The bearings can absorb radial forces, axial forces, and other mechanical loads in order to maintain the stability of power transmission. If you look closely, you can see the inside of the drive shaft is hollow. This design has an advantage. The wires or cables used by the equipment can pass through this channel to make electrical connections. At the end of the drive shaft, a shrink disc is also connected, tightened with a sleeve connecting the drive shaft with the gearbox behind it. It belongs to a high-strength keyless mechanical connection. Next, the power will be transmitted to the gearbox at the back. The gearbox uses a 3-stage gear transmission. The first stage is a planetary gear. The second and third stages are multi-stage gears. Finally, through gear transmission, it can increase the speed to 100 times the input speed. Behind the gearbox, it is then connected through a coupling to the generator. The coupling has a certain degree of flexibility and can tolerate a certain amount of offset. This connection method allows between the gearbox and the generator to achieve complete electrical isolation, because the coupling is made of non-conductive composite material. Next, the one at the back is the generator. Once the power from the drive shaft comes over, it will drive the generator's rotor to rotate, thereby driving the generator to produce electricity. It should be noted that when wind speed increases abnormally, equipment fails, or maintenance is required, at this position behind the gearbox, there is also a brake which can stop the windmill directly. Additionally, because mechanical rotation generates heat, therefore the gearbox and the generator become the 2 main heat-generating components. In order to cool the gearbox, a radiator is installed at this position in the nacelle. The radiator fan will suck in air from the inside and then discharge it to the outside to dissipate heat. As for the cooling of the generator, a heat exchanger is used. The heat exchanger and the generator will form 2 independent air circuits. Under the action of the fan, the internal air will circulate to absorb the heat generated by the generator's windings and then flow to the heat exchanger for cooling. At the same time, the blower will also suck in cold air from the outside, which can also cool down the generator. Combining inside and outside ensures the generator works at a normal temperature. There is also an anemometer at this position. It can continuously detect the wind direction, and then, based on the wind direction, the orientation of the windmill can be adjusted. Let's see how this is done. Between the base and the tower, there is a large diameter bearing. The inner ring of the bearing is bolted to the base, while the outer ring is bolted to the tower. There is a ring of gear teeth outside the bearing. It meshes with the gears of 4 motors. This is the same as what we mentioned earlier about the motors that adjust the blade angle, but the speed ratio of these 4 gears is larger. 3 planetary gears are used. Inside, the resulting massive torque can change the direction of the entire windmill. After talking about the upper part of the wind turbine, let's look at its tower. The tower is the support for the entire generator set. Its diameter gradually shrinks from the bottom up, and the inside of the tower is hollow. The height of each tower can reach over 90 meters. In order to assemble the tower is generally composed of 3 to 4 parts. Each part of the tower is connected by bolts. Depending on the design, the diameter of the tower is usually around 4.8 meters. Inside, it is ladders and elevators for technicians to enter for internal maintenance. At the connection of each tower section, a platform is installed, used for resting or checking if the connection bolts of the tower are corroded. The whole body of the tower is coated with a special white paint to prevent the tower from corroding after being wet by rain. Generally, the service life can reach 20 to 25 years. The power lines of the generator, control lines, or other data lines will pass through the tower all the way down to the bottom. There is a control unit here. The control unit can monitor and control the operation of the entire wind turbine. Since the voltage generated by the generator is 690 volts, this voltage is too low to perform long-distance power transmission. To solve this problem, at the bottom of the tower, there is also a step-up transformer. It can convert the voltage into a high voltage of 33 kilovolts before finally being sent out. Additionally, since wind turbines are too high, they would definitely be damaged by thunderstorms, the electronic equipment inside the wind turbine. Therefore, at the tip of each blade, an independent lightning arrestor is actually installed. The lightning arrestor will guide the current all the way down into the ground below the foundation. Below the foundation is a steel frame composed of reinforced concrete. The steel frame, through special welding, can become a huge continuous conductor. Then, the steel frame is connected to the outer ring electrode. The electrode is made of copper, usually buried 1 meter below the ground. At the bottom of the ring electrode, a circle of grounding rods is also connected. The length of the grounding rods is 2 to 4 meters. They are driven into the subsoil with better conductivity to effectively direct the massive current generated by lightning strikes into the ground.